temperature, shallow geophysics and cone penetrometer, what it is, it's this remote sensing of the subsurface. So we can do geophysics, we can do drilling, and I'm going to review some seismic methods. CHIRP, which is a kind of a high-frequency seismic method, more for marine or lake environments, but has been used for paleoseismology. Georadar, electrical resistivity, so just a few examples. You can have an entire class on this subject. And then I will talk about cone penetrometer testing. A lot of this is the CPT is because we have an expert who actually did her master's on CPT use in paleoseismic studies, so it's easy to make this presentation. And just to make a point that as we move into this part of our lectures, more of the materials that I'm presenting are coming from another textbook, maybe my second favorite textbook for the class besides the tectonic geomorphology one, which is called Paleoseismology by James McAlpin. And it's an excellent book, very complete. And so we have some figures from McAlpin. Okay, so this approach is this remote sensing of the subsurface, geophysics and drilling. So the things we may want to do is to define the shallow stratigraphy and structure. We can go deeper than we might access with trenching. And we can detect buried faults. So it's kind of provides some context around the trenching study as we zoom into more and more detail. And the depth scales can be just a few meters, so in the sense similar to what trenching does, to a few kilometers. So we may even link the surface structure to deep crustal structure. So first one, the seismic reflection. So many of you probably know about seismic reflection, have taken classes. We have some of our colleagues who are here, and other days the geophysics guys are very knowledgeable about seismic methods. And so the basic idea is to send an impulsive seismic signal into the ground, and it reflects from interfaces of different seismic velocity. And so the geometry is for acquisition is very complex, many different ways of doing it. You can do simple zero offset, so just shoot and get the first return, give some distance. Of course, we need to know the velocity of those materials. But if we know that velocity, we could get a depth. And then if you go along that zone and you can keep penetrating these seismic waves, you may show a change in depth, right? So then the usual way, though, is instead of having a single source and single sensor, is to have usually a single source of many sensors, so the geophones, and this spread then lets us look at the refraction of the waves along interfaces and their arrivals at the geophones, as well as the reflections. And so we can have, this is a simple case. And for the kinds of questions and applications that we have in for a lot of active tectonics, we're looking at shallower targets. And so we tend to use sources like this, like a hammer, or sometimes small dynamite, or like a shotgun source. Or another time we use drop weight, so a heavy mass on the back of a truck dropped, and then it triggers the sound as well as timing, get the arrival times at the geophones. So, whereas when you want to go to deeper targets, then you have to put more energy in. So in the petroleum industry, they may use big trucks, big dynamite, and some of the trucks use, instead of a single source, they use vibration, so steady vibration to set up a standing wave that may give better resolution. But we don't usually see vibrosize, that method, in the kinds of work we're doing for active faulting studies. More of this shallow approach. So looking for interfaces, multiple interfaces, so multiple, single outgoing signal, multiple returns. And so then you can also try to increase the signal strength by moving the source and receivers along with overlap. And this is called folding, and the data you can do stacking to increase the signal. So I won't go into any of the data processing. It's well-established field, but beyond our area for our lectures. So here's an example from a fault scarp, and so the scarp is here, so they wanted to see what was down there. So they put the line, these are the flags of the geophones, they're very close together, and also with the hammer source. So this person you see is holding the hammer here. So he's hitting a plate and sending the signal through these, through the geophones. And he may do it like 10 times, and then he can stack the signals. And so you may get something like this. This is not the same site, but this is you see here, this upper one is the post-stacking migration. So there's been some processing applied to clean up the reflection data. And you can see the distance here is 80 meters and the depth is going down to 50 meters. So there's some coherent reflections on this downthrown side. So probably there's some good stratigraphy there. And you see then the trench is just this white outline. So it really shows that how the geophysical approaches can provide this context around the trench and how it's so difficult for us to really access very much depth in trenches, even though this is a big trench. But and also at the same time, our ability to resolve things from in the geophysics is poorer. So, these are good reflectors. There's some disruption here. This is a weak disruption. There are some other disruptions in the footwall, and so they try to trace those disruptions into things they see in the trench. This one's then the tomographic, so it's a velocity model, and it doesn't show a lot. You see some edge effects here. These are just from the model interpretation because the waves are really just going through this part. And so you see a little bit of lower velocity in this basin, but it's difficult to interpret, and with all the lines on there, you say, oh yeah, I see something, but if you take the lines off, it may be quite difficult to have a unique interpretation. So that's the big challenge for geophysical methods. What actually is down there? So here's another one. This is another big trench, 60-meter long trench in Wasatch, so a normal fault system in Utah. And here's the excavation, and then through the same area they did their seismics. And again, you see this log has the interpretation on it already, so it's hard for us to really assess the quality of the interpretation. But it looks like here where the main boundary faults are, especially right in this area, there may be some breaks with depth, but I'm not so convinced that there's a lot to see in this seismic image. Any comments? Anybody a big expert of seismic reflection in this room? Or anybody done seismics? No. In the course, yeah. So it's sometimes ambiguous, most of the time ambiguous, but sometimes you see something that helps you. So it's hard to get, it's not like a perfect picture of what's down there. Perpendicular. So the fault goes like this. So this line may be, it'd be probably something like this. So the seismic line comes across, and this scarp here would be the same as this scarp. Maybe the same place, although there are different papers I see. So here's another one. So the last few examples were normal faults. This is strike slip. This is a Dead Sea fault in Israel, and it's across a dry lake. So there should be good reflectors. And again, it's interpreted. Usually, if there's more space, we try to show the uninterpreted reflection image and then the interpreted one, so we can really be confident about what we're seeing. But here you see this multiple fault zones, and they've drawn it partially because of the interpretation approach to show with this kind of flower structure type model. So you see all the faults are rooting into a single interface. And so we see, three main traces and then the bifurcation up dip of these multiple traces. So this is a common geometry that's interpreted for strike slip faults. So generally high angle faults, but up dip splaying. There's Mohammed, our seismologist, doing some seismic reflection for you. So here, this is a good place because of the lake. Lake sediments are usually very fine and have good contrasts, maybe going down, and so we can, and also good acquisition environment. It's just a flat surface, so we don't have to do the static corrections for changing elevation of geophones. So, and in this case, this is distance, so this is 600 meters, and if there were no clear surface indication of the faulting, then this would be a way to guide further study. So, they show these three zones. So over here, we may say, all right, there's not much to worry about there. Let's just go and focus in this zone or the middle one or this one on the left that indicates, and maybe focus on the one that has the most deformation. So maybe this left one. And that's the value of the geophysics. Yeah, when you actually do the work and you're very familiar with it, then you start to gain a real sense of what you can interpret and what you can't. And then you may grow in confidence. But when we first see it, you just think, I don't see anything there. It's just, but I don't want to be overly critical initially. Like when you're more familiar, you may say, no, that's a very clear break. But sometimes it's difficult to only just use the geophysics by itself. So what would be very helpful is to have a core here or a CPT profile so we can kind of look for what the interfaces may be and tie it back into the interpretation. So there's a trade-off. It's not so difficult to gather these data, but the level of detail is not that great either. So it's useful to do, but then you can easily. Well, here's the topography. So it would just be very gentle scarp, this antithetic scarp. This scarp obviously is, this is a big scarp, 4 or 5 meters high. This is a weak scarp, 2 meters over 25 meters, so it just barely can see it. So in that sense, the trenching shows, yes, it confirms, especially right in this area, that there's really an offset, almost a meter, but there's been erosional modification above it. So then when you go into the seismics, you might interpret as they have that there's a bigger disruption in this area. That I don't see so much there. I guess maybe here's a break. Sometimes, so the way that the seismics are interpreted is you're looking for discontinuities in the reflectors, but sometimes the faults are so important breaks that you get these, they call these diffractions off of it. So you would see some little arcs coming from down the fault zone, and that helps to identify it in some processing. But, these are maybe average examples. I think there are probably better examples where it really works well. And then there are some worse examples where there's nothing to see, and this is medium quality. This is pretty good. I think it's interpretable. So one of the problems with seismics on land is the coupling, so the signal coupling to the ground, we call it. And the second one is the topography. The statics are very hard. So it's much easier to do seismics in water. And so we see the biggest application, marine seismic profiling, but also lacustrine, so in lakes. And so I bring this up because this is some newer technology also, a high frequency, it's called the chirp method. And you can resolve maybe 10 centimeters or so offsets in fine-grained sediment at the seafloor or lake floor. And it's been applied in lakes, but also in shallow marine environments. And so this could be something to try here in Indonesia. So just as an example, this is Lake Tahoe. So we can fly to Lake Tahoe because you can maybe see where it is from ITV. So we start here, take a trip. Everyone sit back, put on passenger seatbelts, we're flying over the North Atlantic. Okay, just a moment. Going to Western North America. We have passports. Well, we have special. You're accompanied by me, so I can speak for you. So here's Lake Tahoe right there, and one thing that they did is they also have really nice bathymetry for the lake. So this is high resolution bathymetry and the hillshade. So this is underwater now. Everything is underwater. And so one thing you can see is these faults, this fault, but you also see these big, huge blocks. So the important thing to see is these mass movements. So these blocks are probably avalanche or just big landslide deposits that have moved out over the floor of the lake. So, and they may be seismically triggered. But there are also the important faults, like this one right here on the lake floor. There's one here, and there's another one. It's hard to see over there, right there. So here we're looking to the south. So this fault zone, nice en echelon faulting. Another fault here. And then these big blocks that are, like 10, 20 meters in dimension fell out of the mountains into the lake, probably causing tsunamis. And so probably earthquake driven. So anyway, there's been, and the Lake Tahoe area is part of, it's kind of a transition between the dextral San Andreas system, and it's a little bit transtensional. So these are normal and oblique faults. And so a lot of effort has been put into characterizing the Lake Tahoe system. And so one thing they did was they used this chirp. So they pull this device. It's called an EdgeTech subscan chirp system. And so the chirp is still sonar, it's still sound, but it uses this sweeping. Why it's called chirp is it has multiple frequencies. It chirps across multiple frequencies, sending these signals out, and they're high frequency, but also because of the greater bandwidth, they can do a more easy job of differentiating the reflectors in the subsurface. And so it's been widely used for these sub-bottom profilers, so for shallow reflection studies. And this one, you see the particular paper I'm talking about is these kilohertz pulses. So here's one example across one of those faults, but also across this big block. And so you can see that this is highly exaggerated, 1,000 meters, but 7.5 meters. So you see very fine resolution in the reflection data on the lake floor. And you can see this nice reflectors showing kind of steady sedimentation, and they're burying the blocks. So these blocks are from this, they call the McKinney Bay megaslide, and you see the sedimentation lapping onto the side of them. And then here's the fault, this North Tahoe fault is right there. So another one, this one is from the North Tahoe fault right there. You see this debris flow. But the nice thing is we can start to correlate, this reflector right here is below these light colored reflectors, and that's probably this one there. So it's just about 15 meter offset. So what they can do is it's hard to get individual earthquakes to really do true paleoseismology, but we can do short-term slip rate studies, but if we can date these sediments. And so they were doing coring, several meter deep cores, but you can imagine slightly longer cores and you could date these sediments. So this dark one here is probably this one, and you almost have the age for it. So you could get a short-term slip rate on this fault. And that would be quite useful. And then you could, if you have a map of it, you can get the length, then you can back calculate the expected slip per event, and you could calculate an average occurrence interval knowing the slip rate and the length. So this is a really spectacular toolkit for us. And these are not so expensive. They can be rented and are used for many applications in shallow water. Yeah. No, it's a very good point. I think it's probably difficult to see the bottom of those blocks. They could be shallow, like around in here, but I think they're all big granite blocks. So because the surrounding mountains are solid granite, and so when you shake them, huge blocks come down, and so they may be hard to penetrate acoustically. The sound wave, the chirp can't go through them, and so we can't see the bottom very well. But it's a really good point that you're making. Is I think, if I'm understanding, is you see this different material and you wonder, is it here or here? What was the level of the lake floor at the time of the slide? Yeah, good question. And I think in other papers they have a better sense of that question. They can focus. Sometimes, this processing for this chirp was emphasizing the shallow record here, but if they process it to try to look a little deeper, they might be able to see the bottom, see some disruption. And I think also there's some other projects that did drilling to find the bottom, to date it. Can't see it. Exactly. Yeah. Very good point. So we don't know this 7.5, so this is a 7.5 meter high almost, or 10 meter high boulder on the floor. And then you wonder how deep does it go? It may not go that deep, because it would be strange if it was a really tall boulder, right? It seems like it's probably more even in its dimensions. So probably the bottom is in this view. We just can't see it. No, if you look in the bathymetry, see, these are these blocks, and so the interpretation is that they came maybe from here. There's these high mountains here, and the mountains collapse in a huge landslide, and these are just avalanche blocks that fell out into the floor. But no, not dikes, no intrusions. They're depositional, but huge. They're 10, 20 meters across and high. That's why they call them the mega blocks. I don't think any volcanism. I think it's only just landslide. Yeah, so I can't do Google Earth here, but I think it's just, these are tall mountains here. So, the lake floor, the lake level is 2,000 meters. The lake is 1,000 meters deep. And these mountains over here are maybe 3,500 meters tall. So from the top of the mountain to the bottom of the lake is 2,500 meters vertically. So if you have a big earthquake, the mountains can just collapse in a huge landslide. But no volcanism. I don't think so. It's all of the volcanoes here are long dead. So it's just an avalanche. Good questions. We can check one thing if you want with these guys, is the size of them. So remember, I'm always giving the commercial for Global Mapper, one of my favorite programs. So here they are. This is the bathymetry. So this thing, 1410 so it's 30 meters high. And here's some more of these guys. So you see 20 meters, this one 50 meters high. So just huge. And then let's see the width. So 200 meters wide. So they're not even boulders. They're like the size of this building that came down to the bottom of the lake. So, okay, let's keep going. But I'm glad you guys like Lake Tahoe study because it's a new study and shows the kind of modern approach. So next one's georadar. So it's ground penetrating radar. Same principles as seismic reflection, except that it's a microwave signal, and the return signals are not reflected from changes in seismic velocity, but from changes in dielectric constants, so the kind of conductivity of the material. And many of you may have done this, but you basically pull they have the sensor and the receiver in the same system, so it's just shooting straight down. There's not usually offset type approaches in georadar. And so that's just pulled in a sled slowly, and it's shooting the whole time. And so here's an example from the, it's 60 meters along this area. This is a thrust fault target. And one thing you can see, they processed out the upper portion because it's probably quite noisy and quite bright. And so this is why this is muted, because there's nothing. They're not showing anything from there. And then in the underneath, they see some reflector from the fault surface itself, probably. And so what they say is the thrust fault is here. You see this layer is offset, and it seems to align with the reflector at depth. So this is a pretty good outcome for these geophysics methods, that we confirm the position of the target structure deeper. So they show this would be 10 meters deep over here, converted from the 2A time. So that's pretty good. Here's another georadar from a normal fault, and you see the trench log below. And here, this bright reflector they see is offset, and another bright reflector. But in their discussion, they say that this underinterprets the offset. So you see the bright reflector is yellow to yellow, but the trench implies that probably the yellow is this orange layer, and it may have been better to come down to the base of this particular layer. So it's the interpretation underestimates the offset because of this maybe miscorrelation, or basically there's syn deposition, or there's faulting occurring, but there's also deposition. So these layers on the downthrown side aren't the same as the layers on the upthrown side. They're thicker. And so it makes for this interpretation a little bit more difficult. And based on the trench, you would probably go from here to here. And that would be a more accurate representation of the interpretation. And then they look at trying to interpret some transition to the more bedrock. And again, they have a smaller offset than the bedrock might imply. So the bedrock offset might be this blue and green to the gray. So, maybe like, what's that, about 3 meters, whereas the interpretation of the offset is only about 1 meter. So in this case, we see the fault is there, which is good, but our ability to interpret and quantify the offsets is more difficult. But it's still there in the georadar. Question? Oh, yeah. Well, no, see, they say acquisition artifact right there. So you're talking about this small offset. This is not an offset, but it means that when they were pulling, they made some small error, or it went down, it somehow changed the timing. So it looks like an offset, but they say acquisition artifact. So there's no offset. They need to actually correct it by lifting all those reflectors. So So the point here is that the georadar, in this case, does a really good job of finding the fault. I think there's no doubt about the fault position. The challenge is the interpretation of the offset and what is happening because the layers aren't exactly the same across the fault because of sedimentation occurring between the earthquakes. So the last of the methods that they present in McAlpin is electrical approaches, so electrical resistivity tomography. And what this one does is usually there's, you may have a source, but you may not. You can use passive or active approach, but you just move over the area with a electrode, basically sensing the resistivity across the zone. And this approach tends to, it has a pretty hard time of identifying sharp breaks because when you invert for it, so the tomography below is this is basically a resistivity map that they made based on their series of electrode measurements at the surface. And when you do that, you don't tend to see sharp breaks. You just see kind of a peak or some gradient across the interface. So it's a little bit more challenging to interpret. But here they say, well, okay, we have this sandy layer, we have a clayey layer that, may be somewhat lower resistivity, implying that it's wet there. And then they think they even see this low colluvium, which is this more resistive material. And then we go down into this late quaternary, and you see here they even interpret a fault, and I don't know if it's plausible or not. So in this case, again, we don't have a very sharp picture of the subsurface, but we do see some changes that might support trenching there. So usually this is done before the trenching, so this guides the location, and then you see that in the end they found a very nice fault zone. So this is from Bulgaria, a normal fault. So, any questions or comments about this? Well, it's always a progression. So you would start with an overview with geologic mapping and geomorphic mapping, as we discussed yesterday. Then you would come to some sites that look like you can generally have a good model for the evolution of that place. Then you do geophysics, basically trying to refine your interpretation. And especially now coming to the question of what's best is more than one method, in my opinion. So you can compare, you try, one against the other. Like this electrical resistivity is going to be very sensitive to, especially the groundwater. So you can almost always tell with, if there's a barrier of groundwater because the wetter side will be more conductive. But then maybe you get good reflections from your georadar, but usually georadar has low penetration, whereas then you may try, okay, we get good penetration from our seismics, so this gives the depth. So what would be good is try all three methods at that place. And then you start to say, okay, we're very confident that the fault zone is in the base of the scarp or in the mid-scarp position. And, okay, we suspect some secondary structure nearby. Then you trench. So it's in my view, this progression. Because the trenching, even though it's quite shallow, it is a test. But sometimes you want to, the time, the trenching is more time consuming. So you commit to making this trench, you may spend 2 weeks or 1 month in the trench, but you can do, with the geophysics, maybe one site every day or two. So there's this also progression of time commitment relative to data return. Usually the gravity won't tell you anything this shallow. It's, even a microgravity, usually you're going to be better. What we've used the gravity for is for basin structure, so upper kilometer or two And so if you come into the basin and you want to see where the bedrock interface is, let's say in a normal faulting basin, the gravity will do a really good job of delineating the overall deep structure, and then that can guide the focus. So gravity, I think, is really great for context. Magnetics, geomagnetics sometimes can be really good. They almost always are easy to do. Most magnetic surveys are fast. And so you can also make a geomagnetic map of a site, and what that does is gives you many observations. And so then if you do a map of the magnetic signal, you may identify some big sources at depth that show where the fault zone is. So the magnetic studies I would put in this area, this classification also. It can work pretty well. For ground-based magnetometer, you can also do airborne, like airborne gravity or airborne aeromag. But here in ITB, is there, or in LIPI, is there some this kind of geophysics colleagues of Lacoste and Romberg? That's okay, it's a good one. So, but you in these research groups, you have these tools, yeah. But also, are there colleagues in the ITB who are experts in the methodology as well that you can collaborate with? Yeah. So this is good because we can learn and be good at it, but also it's often, this is the situation where usually it's good to have collaborators because they may be really experts doing it all the time, and then they may want to refine their methods and learn some things about how it works, and then the paleoseismology or active faulting team gets better results. So often I see this as a collaborative activity. But other times groups will own these tools. Okay, so let's keep going. So another remote sensing method is to go down there. And you can drill, so doing different kinds of drilling, coring. Sometimes I don't show this here, there's large diameter boring. So you can drill holes that are 1 meter diameter, and people go down in and they can interpret. So this is done sometimes. But in this case, I'll just show the example because Gayatri's expertise is a CPT, so cone penetrometer. So the basic idea is you have a truck, it's a heavy truck, and it pushes this rod into the ground, and it has a tip on it, and the tip it's pushed at a steady rate, 2 centimeters per second, and it can sense the friction on the edge, and it also senses something about pore pressure and the overall resistance to pushing to the drive. And so then you get because of the steadiness of it, you can get a measure of the relative amount of friction. And so with materials that are more clayey, you tend to have higher friction, as you might expect. The clay grabs. Whereas if it's sand and gravel, it'll be low friction. And so it's fairly routine to then interpret these friction ratio profiles in terms of the underlying lithostratigraphy, so the changing rock types. And it's the nice thing, as I said, it's a fairly standard approach. It can cost some expense to rent the machine, but once you have it, you just go. And usually they have onboard interpretation, so it's easy to see the results right away. You can try again if there's a problem. And so there's different trucks you see. And again, often like in many places, there are companies that you rent the truck from. They provide the engineer and the operator, and you just say, okay, go, let's do a profile. So guys, do you remember how much you guys rented your CPT machine for? 5,000 per day. Yeah. So how deep can you push it? 15 meters in certain sediments. Yeah. So the thing about these is that they're fairly common because it's a very common civil engineering tool for site assessment. So it's not just active faulting. So there's lots of locations. Yeah, so it's a good method, and it's just like a lot of the geophysics methods. You just have to use it a lot, and then you get used to it. You say, oh yeah, so now we know it's experience, and you can go. So just a review of Gayatri's work. So they were working on this San Jacinto fault, part of the San Andreas system, has a right step, so it's an area of subsidence. And they wanted to explore the development of this step over. And so they dug trenches, which are the black lines, the faults are red, but they also did these CPT lines across the zone. And so here's the place. You can see this really long trench here. And so then you drove along next to it with the truck, right? And then here's the deep trench. So again, this combined approach. So you may do CPT, but then you can dig at the same location, and you can kind of do a ground truth or test what you're seeing. And so here was the nice thing. Gayatri could show with the trench log. So this is 50 centimeters, and you could see a little bit of the change in her friction ratio profile, and some sense of the relationship between the interpretation and the friction profile from CPT and the very detailed logging. So, she sees like coming from up at the top here, this sharp transition in friction, steady, a little dip here in the middle, another one here. So the point is that it's hard to, with the CPT, you can, even though you're measuring friction every centimeter or less, you may only interpret layering that's more than about 10 centimeters thick. So we don't get the very, very fine structure, but we get the gross structure. But we can go deep. So here you see Gayatri's hard work from her master's thesis, and you see the depth. So look at the nice depth. It's as much as 35 meters deep. So there's no way we can dig a trench that deep. And what's very impressive is the ability to interpret the stratigraphy across these faults. Now they're dextral normal, so there some strike slip, but mostly the basin is going down over time. And so you see this, what you'd say growth relationships, right? As we go to the basin, the layers are getting thicker, and even some interbedding of these fine-grained layers. And so she could really, you see, she worked on this to have a variable spacing. So some spaces are large, like this is 20 meters, 25 meters, 25 meters, but then in here it's like every 2 meters or so to really get a high resolution view of the changing stratigraphy. And then, okay, we're in the basin, back out here like that, right? So did you do this in multiple passes? Did you go back and do this, or did you know the fault was there? So this is interesting. So you can go both ways, right? So I was saying in general, you use a tool like this to do the trench sighting. So it gives you a sense of where to focus. But they already knew the faults were there, so they dug the trench first. So then at the top, they could say, okay, these are the zones. Now let's put detail around them. So you go in a circle, kind of, CPT trenching CPT, CPT trenching around and around to focus. So, and then the other thing that this lower one shows is the stratigraphy, just in units, versus the accumulating vertical displacement. And so you can see where that faults are active when. So this big fault here shows the most accumulated displacement between each layer. And so one way to say is this is from one earthquake to the next, but it's difficult to be sure that it's just one earthquake between each of these layers. But it's more like, you could have a few earthquakes, but in that time between the deposition of this layer and this layer, there was, some more faulting. And so that's what this length shows here. So it's a nice graphical way to say also where the big faults are. So, this 1E is the biggest fault in the system. And also it's been active the whole time. Whereas these guys don't appear to have been active early, right? They came active a little later. So that's a nice way to interpret the story and to really pull a lot out of this record. So here's another one, CPT2, similar in general, not as focused faulting, 300-meter length, and a couple of major faults, 2E, this one here is a big one, and then some steady motion on 2B. So, and then maybe deep down here, 2F and 2E are the ones that show the oldest faulting. So, anyway, this is just an example. There's many things. Like I was wondering, you know, if you could go to Lembang with a CPT and just go like crazy around there to try to see what was under the ground. What do you think? If you could go 35 meters, it would be nice. I think. So it's more just she's seeing prominent changes in material. So I think the way is if you go up here. Oh yeah, here's a good one. Sorry. This. So like Mudrik, you see this green layer. It's really associated with this big change in properties, and so she may start by finding something like this as the anchoring unit or anchoring marker. So you say, okay, that's the same layer across everything. So then, and you assume, you know, all you have is the holes, and so all you can really do is if it's not at the same elevation, you just can put a fault between. You don't know where the fault is precisely. But yeah, it's just based on stratigraphic continuity. But the one thing that she can show also, which is interesting, is that the layer seems to get thicker. So, which is consistent with the basin increasing sedimentation rate. So, you know, like here's another one. See, the orange is another one with that kind of behavior. So I think you would do it multiple approaches. So you first set up the overall structure. What are the big features? What are the ones that are really identifiable pretty much everywhere? And then you can go back and you say, all right, well, I know I'm between green and orange. And so then in detail, you say, oh yeah, I think I can see a change here, change there. So some of this detail may be more ambiguous. Like there are other ways to interpret it, but this is the best, you know, that she can see. And you're using these two, but didn't you also, there's another, do you only interpret off these two, friction and pore pressure, or? So that's why it's a whole master's thesis, right? It takes a lot of time to build the interpretation. All right, well, that's the end of this lecture. So just this remote sensing. So what I hope you can see is that very useful, but sometimes ambiguous results. Good to use as many methods as possible so that you can trade them off against each other. But it gives you that intermediate view, something deeper than the trench usually, but not so big as the whole fault zone.